Good morning, everyone. My name is Huo Chen, and I'm a postdoc in the Applied Computing for Scientific Discovery group. Today, I'd like to talk about the work I'm working on at LBL, which is the parametric amplification of a quantum transducer. Let's get started. First, I would assume most of my audience here today is not very familiar with this topic. So I'd like to start with the basics. Why do we need a quantum transducer? To answer this question, I'd like to begin with the story of quantum computers, and hopefully everyone here is more or less familiar with quantum computers. In short, quantum computers are supposed to be the next generation computational devices built upon the principle of quantum mechanics. They are supposed to have much more computational power than the classical computers, thus can solve hard problems otherwise impossible to solve using today's technology. There has been a lot of progress in this field in the past few decades, and perhaps one of the most well-known ones is the demonstration of quantum supremacy done by scientists at Google. Here in this picture, it is the superconducting circuit used by Google scientists in the quantum supremacy experiment. With all the amazing achievement, however, a fundamental challenge still remains in this field, which is the scalability of the computing platform. Let's take the superconducting circuit as an example. This is a very dedicated device that need to be placed into a dilution refrigerator and kept at sub-Kelvin temperature. Imagine if we want to have a practical quantum computer to solve a real-world problem, we would probably need thousands or even millions of those. To host that many superconducting circuits, we would need even a bigger dilution refrigerator and perhaps exponential growing wire connections. Those are extremely hard to engineer, so what are possible solutions? One possible way to solve the scalability challenge is through the quantum internet. Imagine if we have a magic device that can convert the quantum state of the R qubit to the quantum state of the optical photon. Then we can effectively connect different quantum computing platforms via optical fibers. Effectively, we will end up with a distributed quantum computing network. So this is how the quantum internet could help us solve the scalability problem. And of course, the field of quantum internet itself is a very active field with a lot of ongoing research. In fact, here at LBL, we have this QuantNet program that is dedicated to build quantum network testbeds for different applications. Coming back to our story, as you can guess, the magic device that could convert quantum information, quantum state, from qubit to quantum state of optical photon is the quantum transducer. A quantum transducer would be a crucial component if we want to have a working quantum internet. So physically speaking, what is a quantum transducer? In this slide, here is a picture of a particular experimental configuration of a quantum transducer. This one is built upon the optomechanical system, where a superconducting qubit and the mechanical membrane are put together between two mirrors. Those two mirrors form an optical cavity that could trap optical photons in the space between them. And based on the theory of superconducting circuits, a superconducting qubit itself is a cavity at the microwave frequency. Here we call this cavity the electrical cavity because the signal coming through the superconducting circuit are electrical signals. So if we stack this structure together, effectively, we would have two cavities, one at the optical frequency, one at the microwave frequency, coupled to the same mechanical membrane, which is effectively a mechanical oscillator. The magic of this device is, by having this mechanical oscillator, we can effectively couple two cavities that are separated by a huge frequency gap. This is extremely hard to do otherwise. In the next slide, we have a much straightforward schematic of the experimental setup. As described previously, we have two cavities, one optical, one electrical, coupled to the same mechanical oscillator. Here, I would also like to remind everybody this important concept of cavity line shift. You can think of it as roughly a measure of how strongly a cavity would respond to an external signal at particular frequencies. So just like the classical pendulum, those radio frequency cavities would have their own characteristic frequencies or cavity frequencies. A cavity would have the strongest effect on external signals at the cavity frequency. So those are all the background needed to understand our work. But before getting into our work, there is another thing I need to introduce, which is how would people usually operate those optomechanical quantum transducers. So this is a three-step procedure. The first step is usually called the preparation step. During this step, two pump lasers are applied to both the electrical and optical cavities. The frequencies of those pump lasers are slightly tuned from the corresponding cavity frequencies, meaning the laser frequency is slightly smaller than the cavity frequency. And the amount of the frequency difference is approximately the mechanical frequency. There are two purposes of the pump lasers. First, later the pump lasers would serve as carrier waves for our input and output signals. Second, those pump lasers would pump photons into the cavities to increase the coupling strength between the cavities and the mechanical oscillator. Also, during this presentation, I will call the pump lasers as control signals for reasons which will be clear later. After this preparation step, next, we would apply input signal to the electrical cavity. The frequency of the input signal would align with the cavity frequency. As we can see here, now we have two signals inside the electrical cavity. There will be frequency mixing. And the new signal at roughly the mechanical frequency would be generated, and it would excite the mechanical motion. Next, the mechanical motion would also modulate our carrier wave inside the optical cavity, thus generate another output signal at the optical frequency. The final step is, of course, to measure the signal coming out of the optical cavity, and roughly speaking, the ratio between the amplitudes of the input and of the output and input signal defines our transduction efficiency. So here is some simple simulation result. We use the experimental parameters reported by this Nature Physics paper, which is the state-of-the-art experiment to date. We simulate the dynamics of the optomechanical system and calculate the output signal versus the total evolution time. Here, in the top left figure, we have the time domain profile of the output signal. So to get the transduction efficiency, we would cut a small slice of the output signal and perform Fourier analysis on it. The figure on the right is a Fourier domain plot of the output signal within this small red region. Here, the blue curve is the power spectrum density of the input signal, and the red curve is the power spectrum density of the output signal. Since we have only a single frequency input, so the transduction efficiency can be calculated as the ratio between the power spectrum density and the input frequency. So we got roughly 48% transduction efficiency, which agrees with the experimental data. One important, interesting observation in almost all the experiment is the experimentalist would rely on constant control signals to operate those optomechanical transducers. By constant control signal, I mean during the preparation step, the experimentalist would turn on the pump laser and fix it at a constant value throughout the entire experiment. Of course, this is the easiest thing to implement in an experiment, but one natural question to ask is whether this is the optimal way to operate on a quantum transducer. The answer is no. In our work, we propose to use the time-dependent control signal to improve the transduction efficiency. In the experimental context, a time-dependent control signal means to modulate the amplitude of the pump lasers according to some time-varying function. As a result, the envelope of the amplitude modulated pump laser would correspond to our control signal. So this is the reason why we call the pump lasers as control in the previous slide. Before getting into our result, I'd like to first talk about the intuition why our scheme works. The principles we rely on is known as a parametric amplification, and this can be demonstrated by a simple pendulum example in this slide. As we all know, given an excitation, a pendulum at the beginning, a pendulum would begin to swing, and if the initial excitation is weak, the swing amplitude would be small and the motion would die out eventually. However, the story would become very different if we keep driving the pendulum periodically while it swings. In this case, the swing amplitude will keep growing until a new equilibrium is reached. This phenomenon is known as the parametric oscillation, and this is the principle behind a lot of single amplifiers in the electric circuit design. In the context of a quantum transducer, a parametric amplified quantum transducer would correspond to a control signal that rotates at twice the input frequency. So we would expect if we apply our control signals that rotate at twice the input signal frequency, we could get similar effect of the parametric amplification, thus improve the transduction efficiency. So here is our main result. Based on the parameters from the same experimental paper, we calculated the dynamics of an optomechanical quantum transducer. And we obtained the transduction efficiency versus the total evolution time. From this picture, we can clearly see that by using the parametric amplification instead of constant control signal, better transduction efficiency can be achieved. So besides the numerical result, We also have a new theoretical result which states that if the following three assumptions are true, the efficiency of the parametric amplified transducer goes to unity. So the three assumptions are, first, the parameters of the transducer is symmetric, which means the parameters of the electrical and optical cavities are the same. Second, the effective coupling strength between the mechanical oscillator and the cavities are small. And third, the parametric amplified system evolved into a steady state. Of course, there is one caveat of this result is that in the parameter region where we can prove things, the parametric amplified quantum transducer may not necessarily have an advantage over the constant driving case. However, this is still an interesting result, which states that in the ideal case, the parametric amplified quantum transducer would reach perfect transduction rate. In conclusion, we demonstrate that by using parametric amplification, we can improve the transduction efficiency of existing optomechanical quantum transducers. The parametric amplification protocol can also achieve 100% efficiency in the ideal case. Possible future direction of this work include, first, to add noise to our theoretical model. All our discussions in this talk depends on the noiseless case, so it would be very interesting to see how the story would change with the presence of noise. Also, the signal to noise ratio is another very important figure of measure besides the transduction efficiency. Second, we would also like to explore other time-dependent control protocols using machine learning algorithms, or perhaps even use machine learning algorithms to tune the time control profile in real time to achieve for better transduction efficiency. Finally, I'd like to offer thanks to my team members, Bert, the PI for the Applied Computing for Scientific Discovery Group, McKenna, my colleague and PI for this quantum transduction project, and Marty, a summer student from Princeton who has been working with us on this quantum transduction project since last year. This concludes my talk, and thank you very much for listening. If you have any more questions, I'm more than happy to answer them.